Thank you very much, Michele. So thank you for having me here. It's actually nice to be back. It's been a while since I was here, so it's good to be here. There's a complicated title which I will try and justify a little bit at the moment, but I just want to go down because I never get to the end of my talks, so I need to thank the people who did the work right at the front. And I'll just say that you're actually going to hear today about work that's been done by Richard Brierley, starting out while he was a graduate student in Cambridge, then a postdoc at Yale, and he's now just become an editor in Nature. Alejandro Lopez-Pesanilla, who's currently a postdoc at Argonne. Jan Guzman was a postdoc at Argonne, now is a faculty at the University of Costa Rica. Nick Bristow was a student of mine in Cambridge and is now currently at Imperial. And other folks I think that you may know very well, Emilio Artacho, a long-time collaborator in Cambridge and San Sebastian, and various other people, particularly Miguel Pruneda and Max Stengel in Barcelona, responsible for various pieces of this work. And of course, without all of these folks, I wouldn't be able to do a management role and still do science, so I'm glad to be able to do that. I'm really going to talk about how to fool around with what we like to think of as functional oxides. Just as an example, what do we do with oxide materials, or what can we do with oxide materials? I will talk a lot about materials with this structure, which are perovskites. And one classic area of these is that you can make materials which are ferroelectrics, and the ferroelectricity can be used as a store of memory. Another very similar set of oxide materials everybody owns in here, they're cathodes in batteries. They appear as electrocatalysts and in fuel cells, conducting oxides. And then there are a few things which it would be interesting to use them for, and they haven't been used for yet. One is electrocalorics. If you've got a material that you can tune through a phase transition with an electric field, phase transitions can have latent heats. And so that means that you can make a Carnot cycle out of them, and you can use them as a refrigerator. And in fact, people do. There are interesting magnetic variants of these materials, which can have large magnetoresistance, and there have been various attempts to use them. And because these materials both have functions in terms of resistivity, electronic functions which can be tuned by moving ions around by this kind of thing, you can basically take this kind of stuff and combine it with this kind of stuff and propose it for new forms of memory, such as memristas. And there are many others, but the basic physics that I want to talk about, and that is in most of those things, all comes from a flexibility of a few very simple ingredients of these transition metal oxides. And I won't get very complicated with structures. I'm going to talk almost entirely either about materials which are perovskite structures like this, or layered perovskite structures, but very similar to this. And in all of these materials, they have this kind of formula unit. So they're oxides. At the center of the octahedra is a transition metal atom. And that transition metal atom is the thing which is active. It may have a moment, so you can make magnets out of it. It may move off center so that you can make ferroelectrics out of it. It may change the shape of the octahedron so that you can make ferroelastics out of it. And the way that I tune the properties here is by doping, and the doping comes because there's an ion which sits at the center here, which is typically either a rare earth or an alkaline earth or maybe an alkali element. And of course, as I go from 3+ to 2+ to 1+, charges will come off this ion and go onto that. And so that is used to dope these structures. And you have a kind of a mix and match that you can play with this, where you can make superconductors like lanthanum copper oxide, ferroelectrics like barium titanate, ferroelastics, ferromagnets, antiferromagnets, charge density waves, ion transporting materials, because ions which sit in the middle of these cages can move around a lot, They're used to absorb light, to make photoabsorbers, and of course to make catalysts and cathodes. So there's a long array of these things. And if you're a materials designer, your goal is to get the set of properties that you would like along with this, and maybe not just to make it in one material, but to make it in several, to make heterostructures, to make layers of these things. And what are the tools are, of course, chemistry in some sense, but what are the design rules? That's sort of written down here, and I want to talk just about some of the design rules, because there are the things that people are doing and that we're getting used to do are kind of different from the way that you would perhaps have thought about it to start with. One point I do want to make is that most of these materials are in the class of what we would call strongly correlated. What does strongly correlated mean in this context? Strongly correlated is that the electrons which are flowing around, typically in those transition metal oxide layers, are small. I mean, what's the sense of an electron being small? Well, how big is an electron in silicon? An electron in silicon is actually about 10 nanometers across. And the reason is that in a material where the dielectric constant is 10 and the effective mass is 1/10, the binding energy of a charge to a positive charge produces a hydrogenic radius which is quite big. So you don't put many electrons into silicon. The nice thing about these materials is that the dielectric constant is of order 1, the mass is of order 1, the binding energy is very strong, so you can pile huge amounts of charge in and out of this stuff. But those electrons see each other because they're piled up very tightly, and that produces strong correlation physics. Because of that strong correlation physics, of course, we have all of those phases, the ferroelectrics, the ferromagnets, the superconductors, which we're trying to play with. And often what we're trying to do is we're trying to tune close to one of those phase transitions, and that can be a pretty delicate thing to do. And so what are the routes to do this? Well, there's a classic one that you may be familiar with in the cuprates. So lanthanum strontium cuprate is the first of the series of high temperature cuprate superconductors. And again, what you're doing in something like this is that you're changing the carrier density. So strontium is 2+, lanthanum is 3+. So as you change X in here, you're changing the number of electrons that sit in these copper oxide planes. Okay? But you can do different kinds of things. If you made a thin film of this, you could apply an electric field and you could gate the system. And that would produce what you would call modulation doping if it was a traditional semiconductor. Okay? Now, as I'll point out, when you try and do things like that, often you discover that you're doing other things that you will tend to be doing electrochemistry as well. So if you take a surface and you modify the surface, the way you modify the surface can add charge. And then lastly, something which people tend not to think about, and I want to point out is very important, is that you can make use actually of the sizes of ions in here. So even just by changing lanthanum to yttrium, even though they're both 3+ ions, they're electrically inert, they have different sizes. The way that the sizes stretch or squash the lattice can really change things quite dramatically. And I will try and get through all of those things in this talk. Right. So let me start. I'm not going to talk in great generality about lots of things. I want to give a few examples which we can discuss. And I'll start actually by thinking just about interface structures between two materials. Two perovskite materials, they have the same structure, lanthanum aluminate, strontium titanate. Both of these materials are insulators. So you might think that if you put two insulators next to each other, nothing much is going to happen, and it turns out not. And let me explain why. And so this goes back to, well, probably earlier than this, but it was sort of first discussed here, and of course is much discussed in Geneva. Our colleague Jean-Marie Tristan and others have worked very heavily on this and done it. But if you take a perovskite material, which has now been simplified here to look at it in terms of these layers. So if you think about this, starting with strontium titanate from the bottom, and we're looking up in the 100 direction, the direction of those cubes, there's a layer of strontium oxide, then there's a layer of titanium dioxide, then strontium oxide. And if you just count the formal valences of this, each of these layers is actually neutral. But if you go up to the top to lanthanum aluminate, which has exactly the same structure, the formal valence that you would normally associate with lanthanum and with aluminium is 3+. And so that means that the lanthanum aluminate layer here is formally positively charged. The aluminum oxide layer is negatively charged. And you see, as I go from one thing here, I go from neutral layers to layers which are now positive, negative, positive, negative. So there is a dipole forming in here just because of the way that I ended that surface. So one way of thinking about this is that there's a natural dipole which ends in here, which ends on this surface. And you should all know that the divergence of a polarization is a charge density. And therefore that means that there is a formal charge which ends on this layer. It's a fixed charge. But because that charge is there, if I now sprinkle in carriers, the carriers will then run to this interface. And that's the idea. And with a number of complexities associated with it, that's basically correct. Okay. So let's imagine making this material, and let's make a heterostructure, a repeating heterostructure of this strontium titanate, lanthanum aluminate, strontium titanate, lanthanum aluminate. And there are, depending on I can end the interface with a positive or with a negative. And so that means that there will be an electric field now which is pointing like a capacitor plate from one to another, this way. That means that if I look at the potential, of course, is the gradient of the electric field. And so there's a potential which will zigzag up and down like this in this pristine structure. And you know, that is indeed correct. And the formal ionic charges give you exactly the right answer for the thing here. And you might say, how do I know that the formal electronic charges are the right things to use? One has to chase that back. It turns out to be essentially a fundamental theorem of topology. There's a nice story around that. Invite Emilio Artacho to come and tell you about it. But believe me, it really is true. So that formal charge is here. But of course, those charges are just fixed. But if I now have a potential in here and I start sprinkling electrons and holes around, they will flow to screen the charges on these plates. And notice also, by the way, that if the voltage difference between these two things begins to exceed the band gap of the materials, then once this voltage exceeds the band gap, then in fact you will begin to deplete carriers from one material and have electrons flow from one side to the other so that they can be built up one way or the other. Okay? Now, by the way, just to prove that it really does work, this is what the band structure calculation looks like if you do it for something like that. Here's lanthanum aluminate, here's the strontium titanate. Lanthanum aluminate is a wide band gap semiconductor. This is going up in the Z direction. So as you see that, so we've got 12 layers of these, and you can see basically that the potential just moves down. This is the potential of the band gap. And here it comes back up the other way. And these are the D bands of strontium. And somewhere around this point, by the way, you notice that the chemical potential lies here. It begins to cut the top of this band and the top of that band. So in equilibrium, charge would flow from one to the other. And then I would have free charges, electrons and holes, associated with this. And so I now begin to charge up this capacitor plate. Now, just a point to make about that is that that would make a very nice battery that would be solar powered. So if this really worked, I could put this out in the sunshine, and the sun would create electron-hole pairs by exciting above the band gap. Those electron-hole pairs would sit in this field and they would just charge up this capacitor. And then if I could find a way of putting a contact on these things, I could use this as a solar-powered electric storage device. And moreover, you know, the scales of the distances here are such that you should be able to charge this up almost at the level of 1 electron-hole pair per unit cell, and that would end up giving you a storage density of the order of gasoline, and so that's why it would be kind of an interesting thing to do. I think this is more inspirational about what you might be able to do than practical, because as I will point out, I mean, this sort of almost works, but not quite. Okay. But keep it in the back of your mind, because there's absolutely no reason that you should not be able to design a battery material that doesn't operate with this principle, if not these, if actually not these elements. But back to reality. So what actually happens, and maybe let's just focus on the right-hand side here, when you make this material, what you can do is that you can measure the conductivity of the electrons at one of those interfaces. And this is resistance versus temperature. And depending on how you grow the surface, what you discover is you get very different answers. Sometimes you get a really good metal. Sometimes you actually get something which is a much worse metal, but still metallic, and in fact, at low temperatures, superconducts. And sometimes you get something which is a much worse metal, but then shows magnetism in here. Okay. I don't want to go into the discussion of magnetism and superconductivity, the resistivity measurement here, but just to notice that actually what happened in this experiment is that the answer you got depended on the pressure of the oxygen at which you grew the material. If you grow at very low overpressures of oxygen, you create a lot of oxygen vacancies. Oxygen vacancies add carriers to the material, and they dope it. Okay? As you make the system closer and closer to the stoichiometry, you get less and less of that physics, but you see that you've already implicated something very different about the way that this might work. And let me give you a thought about how that would happen. Okay? So rather than thinking about the ideal situation that I drew, let's ask why that might happen. So if I have a substrate, for example, and on top of it I'm going to grow a new film. And here is just the sort of the growth direction. This is energy along here, valence band, conduction band, and the solid line being the chemical potential. If I have a charged interface, at that charged interface, as I grow further, there's an electric field, and therefore the voltage increases. And what I just described to you as the conventional picture that would happen is if I grow thick enough, eventually this valence band will exceed the chemical potential. And at that point, what will happen is that electrons will move out of this valence band and they will come over to the conduction band. And so that'll generate a modulation-doped electron gas here. And I'll generate a modulation-doped whole gas at the surface. Nobody ever sees the whole gas. Why not? Well, one of the processes that can get in the way is to think about, as you're growing, there are other things that could happen. So you have a surface that you're growing and you're depositing all of the time. Does it want to be stoichiometric? And why might it not want to be stoichiometric? So one simple thing is just to think about what would happen is if you lost an oxygen atom from the surface. If you lose an oxygen atom, it's naturally an O2 minus in the structure. So if you take an atom away, you're going to leave 2 electrons behind. Those 2 electrons would normally go into a rather shallow state just below the conduction band. Now, of course, if those 2 electrons are created up here, you will lose them and they will run all the way down the hill and they will end up here, and eventually you will end up with an electron gas here, but an insulating surface here, with a set of empty vacancy states in here. Now, there are other reactions that I could do with this, but I just want to focus on the oxygen. So the question is then, which wins? What is thermodynamic? So as you grow thicker and thicker, of course, you will understand that these charge layers are getting further and further apart, and therefore the Coulomb potential costs you more and more energy as this grows. As you're doing this, you pay the energy of a vacancy, but you cut down the Coulomb energy because you screen the interface. Okay? So there's a very straightforward calculation that you can do to balance the Coulomb energy versus the energy of creation of a vacancy. That's done here, but you sort of imagine this in your head. There's a vacancy energy cost, there's a defect, there's a Coulomb cost, and there's a critical thickness that will happen that will turn up where it's favorable to have vacancies or other reactions forming at an interface which produce the doping and produce the screening. Okay. Where does that happen? It typically happens around 2 unit cells, much less than the 4 or 6 unit cells that you would actually need to have your favorite model of this. I don't want to go through all of the details of that, but I just want to point out then that you thought that you were doing electrostatic doping, and what you ended up doing, in fact, was electrochemistry. Okay. So when we're dealing with these structures and with these devices, you should understand that it is very natural to think about chemical reactions and electrochemical reactions at the same point that you're thinking about standard electrostatics, and it's important. Okay? And by the way, that brings me to thinking about batteries. Okay? So on the one hand, we're thinking about the first part of that discussion was driven by the idea of thinking about how to make new, say, electronic devices. But what you discovered is that actually electrochemistry matters. Okay? So let me tell you a little bit about battery basics. Okay? So if I want to make a good battery, I need an anode, I need a cathode, and I need an electrolyte between them that can produce, that will allow ions to transport but will not allow electrons through them. So the voltage that you have in your battery is the difference between the Fermi energy in the anode and the Fermi energy in the cathode, because this will be the voltage that will be established in the external circuit. Okay? So if you now think about what I want to do to make a good battery, I would like to have this energy as big as possible. I would like to have the density of states in these two bands also to be as big as possible. Why does that matter? Well, that matters because the capacity of the battery, the number of electrons that I can take out from here and put back in there, is related to the integral of the density of states in the band, assuming how far I can move it up. Okay? So I want things with a big density of states and a big voltage. So if you know something then about transition metal oxides, so by the way, in the Sony battery, so-called, you have the anode is made of graphite, the cathode is made of lanthanum cobalt oxide, or something like this. So again, it's one of these transition metals, and sorry, it's lithium cobalt oxide, and the working ion that runs between these has to diffuse in there as lithium, is shuttling around from one to the other. But if I want a good battery, so what do I need? I want high density of states and deep levels in the cathode. So if I'm working with a 3D transition series, that tells you go all of the way to the right, because as you go to the right-hand side of the D transition metal series, the D levels move down. That's the contraction that happens as I go across any series. So you'd actually like to go from manganese to iron to cobalt to nickel. And if you look at battery technologies as they've advanced over the last few years. That's exactly what people have tried to do. Similarly, you'd like to get a high density of states with the anode, but that's tough to do because, of course, you can't get the chemical potential on the anode side above the vacuum energy. So you want something which is very high in energy, but it can't be above the vacuum. So the natural thing to work with elements like carbon, which is why there is graphite. But lithium, by the way, doesn't go very far into graphite. As I put more and more lithium in this, the chemical potential moves up, and it hits the Fermi energy will hit the vacuum level at a doping of about 1/6. So you would like things which had a tighter density of states, or you'd like to put different kinds of ions in here. Okay. So that sort of gets you to the materials that we have now. So, as I say, the commercialized battery in 1991 from Sony is based on lithium cobalt oxide on the cathode. So that's not a perovskite, but it is another layered oxide. And the lithium shuttle in and out of here, and they shuttle in between the layers of graphite. And you can't get further than LiC6. And you can't get much more than a half of lithium cobalt oxide. Okay. But both of these materials, as well as having useful battery characteristics, turn out to be quite strongly correlated materials because, as I say, the electrons are there. So battery people like to think about this. If you're a condensed matter physicist, you worry about things like this. So there's a famous material, sodium cobalt oxide, very closely related to this, that becomes an anomalous superconductor at low temperatures, and it actually has ordered phases of vacancies associated with that. And if I go from lithium to calcium, calcium is charged 2, so I'd like to be working with an ion like calcium rather than an ion like lithium in a battery. But this material actually produces an ordered density wave state at about room temperature, and also is an enormously high temperature superconductor, around 12 Kelvin. Okay. So there's an interplay between the materials that we want to use for one class of technologies and the problems that come across for the other. Okay. And what you're running into here, in this case, is what I would call Mott physics. Because the phase transitions which are happening in some of these structures are phase transitions in which carriers become localized, and those localized carriers form new phases, and those new phases are often insulating. And because those phases are insulating phases are not very good things to make electrodes out of. The first thing you need from your electrode is that it be a metal. Now, watching the time, I'm going to skip forward through the next bunch of slides because I don't think we need to see this, but I could talk more about it later because I wanted to move to something else. But just to show you, actually, this is the Sony cathode material. This is the phase diagram of that material, or some part of that material. You're starting over here, but as you begin to move across here and dope it, you run away from metals to insulating phases, to another insulating phase, to other kinds of weird stuff going on. This may be interesting if you want to find interesting phases of matter. It's a very bad thing to be making a battery out of. So one of the challenges that you face, actually, if you want to work with these to make battery electrodes out of materials with transition metals, as I say, to the right-hand side of the periodic table, so that the voltage is big, you get to a point where you have flat bands, and flat bands is, of course, where you have Mott transition physics. Now, so I talked a bit about electrostatic doping and electrochemistry, and pointed out how closely they tend to be related in these systems. I now want to switch to the last item on my list, which is size effects. Okay. And why might one matter? Okay. So I just introduced the idea that one of the problems that we're having with wanting to use battery electrodes made out of lanthanum nickelate is that lanthanum nickelate is in fact an insulator. Okay. And that is a classic case of a correlation-driven phase transition. It's not something that you would find in the standard band structure. It happens only because the Coulomb interaction is important. Now, a paradigm for that, for physicists, is to think about a model which is broadly called the Hubbard model. And this is just the hopping of free electrons on a lattice given by some hopping parameter. So this is the electronic band structure, if you like. But then an energy penalty that you pay of just the Coulomb interaction of having two electrons on the same site. So what we know is in a model like this, if U is big enough in comparison to the bandwidth, this term will dominate. It will prevent two electrons being on the same site, and I will localize into some kind of insulating phase. Now, but this is, in fact, very generic. While you might often see the Hubbard model written down, there are many, many different possible broken symmetries that can happen when you have complicated materials, because materials have spin, they have orbit, they have space, they have lattice, they have charge, and so there's all kinds of phases which occur associated with this. Okay. And so many, many different kinds of broadly what I will call Mott transitions. But, for theorists, at least theorists of my ilk, the standard dogma is that what really matters when you're designing materials is just the ratio of the interaction to the bandwidth as a parameter, the number of carriers in the band, because obviously there aren't any carriers in the band, it'll be an insulator anyway, and the fact that there are all of these other couplings and broken symmetries, and in particular the coupling to the lattice degrees of freedom is sort of mostly irrelevant. Okay. So that's the sort of central dogma of thinking about these things as electronic phase transitions. Okay. So I want to try and disabuse you of that. Okay. But here's a sort of a classic broad phase diagram of all of those transition metal oxides that we're talking to you about, going across the transition metal series from D0 to D8. So copper is on this side, nickel, cobalt, etc., going down here. And it's a complicated diagram, and sorry, you can't see it very well, but what's generically plotted on here is the ratio of the interaction strength broadly to the bandwidth. So if you're at the top over here, you get insulators of various kinds. And if you're at the bottom, you get metals. And then as you move along these lines across here, you're doping, say, between D2 and D3 or D3 and D4. And this is real data. And what is interesting that as well as being able to cross these phase boundaries by going from left to right, you can always cross them by going from up to down. Okay. Well, how are you varying this parameter independent of the doping? Well, one way you're doing that is you're varying it by changing the size of ions in the unit cell. I drew you a cartoon of a perovskite structure which was absolutely cubic. So here are those octahedra, here's the active transition metal atom, here are the oxygens around it. When the electrons hop around in these structures, they're hopping from one metal to another metal via an oxygen in between them. And so there's a coupling here, an electronic coupling between this thing. And of course that depends on the overlap of these orbitals. And there's an angle in here, and that angle doesn't have to be 180 degrees. What changes that angle? Well, there was a hole in the middle in this structure, and that's where the rare earth ion was, the lanthanum. If I pick a big rare earth ion, what I do is I push out this structure and I make this bond very nearly flat. If I have a small rare earth ion, what happens is it folds up because there's too much space, and I get sort of puckered, rotated lattices. Okay. And so, sort of a simple thinking says, well, okay, what I'm doing is this ion isn't changing, so the interaction strength isn't changing, the doping isn't changing, but the bond is changing, and therefore I must be changing the bandwidth, okay, as a function of angle. And indeed you are. However, it doesn't look like you're changing it very much. So here's one class of materials, manganites, that I will talk quite a lot about in a moment, where the transition temperature for one of these Mott transitions varies from above room temperature to 0 by changing the cation radius by a little bit. But if you calculate the change in the bandwidth, it's only 2%. And it's kind of remarkable that that 2% change can produce this big one. And by the way, something very similar happens in the in lanthanum nickelate. In the nickelates, lanthanum nickelate is actually out here. Lanthanum is in fact a metal all the way down to T equals 0. Everything else here is an insulator, but the transition temperature changes by 600 degrees with very small changes in this angle. And it seems to be a little bit odd that everywhere, everywhere on this phase diagram, I can go up here, I can go up there, I can go up there. I'm making 2% changes in the bandwidth, and I always hit a boundary. Seems unlikely. So is there another way of doing this? Okay. And of course, there is another way of doing. I think there's another way of doing this. I wouldn't be standing up here and telling you. And that's because there are other things going on here whenever I have a Mott transition. If I have a Mott transition in the manganites, actually what happens is that the shape of this octahedron changes. But actually, each octahedron is connected to another octahedron. So when one thing moves, the other thing has to follow it. And that produces long-range elastic couplings, and those things can be really important. And to explain why they're really important, I want to just work on a toy problem which makes quite explicit the mathematics behind that. Let me take a ferroelectric material, Theoris ferroelectric. Above the transition temperature, it's square. I can only draw things in 2 dimensions. So if I look at barium titanate at very high temperatures and I look at a crystal of it, it will have square symmetry. If I cool it down, it will establish a spontaneous dipole moment, a polarization moving in here. And what that means is that every titanium atom in every unit cell moves in the same direction by a little bit, and that generates a set of dipoles, and they all add up, and that produces a macroscopic polarization. Okay? But when I do that, the crystal will also change shape, because there's a direction associated with it. Everything moves there. So macroscopically, actually, the crystal will change shape, and you can see this. Now, actually, you very rarely see single domains. Typically, in a crystal, you see something that looks like that, sort of these letterbox pictures, which consist of little domains. These can be large, they can be small, but I'm imagining that they're pretty much macroscopic, and they will form in a material like this in these kind of patterns. Why do they form in these kind of patterns? Well, there are 2 reasons. So here I've got a polarization. Here I've got a polarization going the other way, and you will notice that this is head to tail. So that means that there's no surface charge that develops in this structure. Okay? Unlike the lanthanum aluminate strontium titanate situation where I had head to head, and therefore there was a charge here. So this is neutral. That's kind of low energy. It likes that. The other thing is, if you just think for a while, you'll also realize that this is the only way that I can join the domains together so that the crystal doesn't crack. This line has to be exactly at 45 degrees, or sometimes this is called a 90-degree domain wall, and this is a 180-degree domain wall here. And those are the only 2 stable situations for domain walls that won't produce cracking. Now, by the way, if you're making a ferroelectric device where you want to have lots of little domains and you want to switch them, that's one of the things that you actually have to overcome to make sure that that works. Okay. But now, if I now think about this, if I look at, say, this domain wall, I'd like to know how mobile is this domain wall. So let me extract it from here, draw it along here, and here's the polarization coming in and coming out and like that. And so as a theorist, the first question I ask myself is, okay, this is an interface. I want to think about the interface moving. I'd like to think about waves that might appear on that interface, just like a wave of water. And that's going to, of course, introduce elastic stress. But the question, the first zeroth order question you might ask is, what's the dispersion curve? What's the frequency of restoring force of waves as a function of the wave vector, as a function of the wavelength? Okay. Now, you might imagine that since this is a flat wall along here, as a wavelength gets very close to, as k goes to 0, or the wavelength goes to infinity, the waves I'm describing are just moving walls. And therefore, I should expect that this would have an acoustic dispersion relation, just like any kind of sound mode. And it doesn't. One page of algebra, sorry, but this isn't complicated, but it might be useful to some of you who like algebra, but this is all just classical physics. How would I solve that problem? Okay. This is the way I like to think about it. How do I describe that? And this is just 2D elastic theory. So you start by thinking about your order parameter. So in this case, it's the polarization. So the polarization has an energy term that looks like this. There's a p squared and a p fourth. And if you know anything about Landau theory, what you will know is that if this coefficient r becomes negative, that means that the energy goes down for a little as the polarization increases, and this term will stabilize it, but there's a minimum of the polarization at finite p. Okay? There's a kinetic term, and then of course there's a so-called gradient term. That's how costly fluctuations in the polarization would be. If I want to make the polarization inhomogeneous, if gamma is large, it penalizes fluctuations from place to place in the polarization, and if gamma is small, they're easy to have. The next term in the energy is just the elastic energy. And so this is the elastic energy in terms of the standard strain degrees of freedom. And so this is the volume strain and two kinds of shears. So this changes the size of the crystal but keeps it cubic, or keeps it square. This is 2D. This turns a square into a rectangle, and this turns a square into a rhombus. Okay. They're coupled, and in this case they're coupled with this term, which is squared a rectangle, coupling to the difference in the polarization. Okay. The term exists by symmetry. That's why when the polarization happens, this thing changes shape. Okay. So that's that term. And then there's dipolar Coulomb terms that I won't play much about. Okay. Now, one very important thing about elasticity theory is, we like to write elasticity in terms of these three independent fields in 2 dimensions, but that's actually one too many. Because if you want to describe the deformation of a sheet in 2 dimensions, it clearly only requires a 2-dimensional vector field, and I've got too many degrees of freedom here. Okay? So these are not independent. Okay? They are related by what's known as an elastic compatibility condition. And it has a sort of a Poisson equation-like form. It says that fluctuations in one field have to be cancelled by fluctuations in the other. And all that's just making sure of is it's making sure that things don't tear when you deform it. So how do I solve this problem? Well, free energies are there to be minimized. So I would get rid of the strain in terms of the polarization by saying, for any given polarization, let me make sure that I know what strain is there. And so I can get rid of the strain term, and I can solve that with this condition on part of it. And of course, because this couples to a square, after I minimize, I'm going to get that phi goes like p squared, and therefore this energy term is eventually going to look like something which goes like the fourth power of the polarization, so it's like a U term over here. But this is what that term looks like, and I have had to write it in k-space because that's the only sensible way to write this. And so here it is, it's a p fourth term, but it's coupling the Fourier transform of the polarizations to itself via a kernel. And that kernel depends, of course, on the wave vectors of the various components which are in here, and that's k, and it also depends on the frequencies of those components in here, because strain has a sound velocity and it moves at a finite rate. Okay. What's interesting to notice if you look at this is that there are as many powers of k on the top as there are in the bottom. Okay. So this is formally of an infinite range interaction. Very different from this thing which is entirely local. This. Okay. So there's infinite range interactions do weird stuff. Okay. It's very anisotropic because it depends on the direction that kx and ky go to infinity. Okay. So what would the mode dispersion look like? Well, it turns out that I told you should expect something which was a sound wave, but actually it turns out that it's k half. This is a tsunami. Right? So this is like a water wave, and at very, very long wavelengths, the velocity gets faster and faster and faster and faster. Okay? Now, that would be fine, except that the interaction which produced this was produced by elastic degrees of freedom. And there's a sound velocity in the middle here, which is how fast those couplings can propagate through the material. And this is just the speed of sound in the material. So everything to the left of here is superluminal. Namely, it ain't right. Okay? So you cannot have, so actually this in fact gets cut off, and the actual dispersion has a gap. Which is somewhat surprising. And it will have a gap, and then it will actually have decay into Cherenkov radiation coming in here. But actually that's something that anybody who works on ferroelectrics knows, because when you switch ferroelectrics, they make a noise. And that's the Cherenkov radiation, which is produced by moving these objects. And the reason this has a gap is that if I try and move this wall fast, the lattice behind it cannot keep up, and therefore it's pulled back. Okay. And that can be pretty substantial. Now, need to close this out soon. So can I get rid of that physics, and does it matter at short scales? So now I need to tell you about why that matters for the Mott transition. I'm going to pick exactly one Mott transition to think about. Let me just run through this. Okay. Manganites have been studied for a long time, and here I'm just imagining doping manganese in this in lanthanum calcium manganese oxide. As I go from 3+ ions to 2+ ions, what I do is I turn manganese from a 4+ ion to a 3+ ion. Now a 4+ manganese in a cubic environment turns out just to have 3 electrons lined up at a deep level, and that produces a large local moment, but it doesn't move around. When I add an electron in here by going from 4+ to 3+, I put an electron in this higher energy state. If that electron hops around, because of Hund's rule, whenever it's on a site, if it hops onto this site, it can only hop if the spins are parallel, and therefore the motion of this electron moving around will align the spins, and it means that the ground state is a ferromagnetic metal. But that's not the only possible ground state. The other possible state that can happen is what happens if this octahedron changes shape, because this is doubly degenerate in the octahedron state. And if this octahedron changes shape, say by 2 oxygens moving in, 2 oxygens moving out, that's called a Jahn-Teller distortion. This energy level is split, and the energy goes down. And that is clearly going to suppress the hopping, and it's going to lead to a nearly insulating state with this. Okay. That's what happens excuse me, in these materials, in lanthanum, strontium manganese oxide, by varying the doping. As you go from very small x, it's an insulator. As you put more and more carriers in there, eventually this ferromagnetic metal takes over, and you have a metallic phase. And this transition here is an interesting one, because from here you're going from something where I've got a metal to something which is really nearly an insulator, because the carriers have been trapped, but they've been trapped into something which isn't ordered. Okay. And so then I should ask, how do you do that? Okay. If you think about the structure of manganites, I say that the basic motif, if it's deformed, has these squares turned into rhombuses. And if I want to dope it with something and make a 4+ ion, I have to find a way of fitting in something which likes to be small and square in here, and the problem is that is connected to that. Now, that isn't easy to do and have this thing move around, because of course because everything couples to everything else. So for example, if I take this thing and I change the shape of just one of them, it's going to move through the solid and move it around. Okay. Is there a way of getting around that? Well, sort of intuitively there really is, because suppose that the ground state didn't have everything perfectly aligned along these axes. Suppose it actually had some rotations built in. And with those rotations built in, you can sort of intuitively feel that if I change the shape of here, instead of forcing the neighbor to change its shape, it could rotate instead. Okay. And so, of course, the amount that it rotates depends on the other ion, which I haven't even shown here, which is in here, which is holding the structure up. So this is an inherently softer structure than this one is, and therefore it's easier to disorder. You can actually make a theory about that, and since I'm running out of time, I'll make you read the paper. But for example, what it really means is if you look at, here's a cartoon of a Jahn-Teller polaron, I just put a single one in the middle of the lattice. By putting a single one in here, what it does is it pushes out and it tries to deform all of the others, and you see that the compromise it produces eventually is to produce this star-shaped pattern along here, where these are the strain fields generated from here, and they extend out to infinity. If I start with a structure which has some rotations built in, those strain fields die off more quickly, and they're absorbed more effectively locally. So this thing is lower energy than that. It's easier to make. You can make a theory of that. And this is the outcome of the theory. It's not a very complicated theory. It has only elasticity in it. And the simple theory for what would happen for the phase transition. So you pick things here to give you a transition between this ferromagnetic state and the non-ferromagnetic state. And then just by varying the radius with parameters that you essentially know, because they're all associated with elastic degrees of freedom, this goes all of the way down. And by the way, it goes the same way with disorder, and all of these points on here are essentially data. Okay. So you've got very large changes in this, because this phase has a lot more entropy, has a lot more fluctuations built into it than this one. Okay. Similarly, the other place where there's a lot of data is in the nickelates. Again, lanthanum nickelate is over here, and there's an insulating to metal transition, which has nothing to do with the onset of magnetism that happens at a lower temperature. And again, you can quite easily produce these very large fluctuations. But in particular, again, what you have here is that, the elastic effects are really controlling the entropy and the entropic fluctuations associated with that, and producing these very big effects and these transitions that you can move around a lot, actually, by strain. There's even some nice materials to look at. My favorite, actually, at the moment is scandium trifluoride. This is a material which is really officially a vegetable. It has, it's a very large gap insulator, but interestingly, it has very soft rotations associated with all of these things, and those rotations seem actually to be diverging very close to t equals 0. This is actually seems to be an elastic quantum critical point. Similarly, strontium titanate is famous for being an elastic quantum critical point. And one of the puzzles, actually, about materials like strontium titanate is why this near ferroelectric behavior, well, in fact, you can drive it ferroelectric by changing from O18 to O16 or with pressure. Why is this phase transition not first order? Because all of the theory that we would have seen so far should suggest that this phase transition should be first order, because the coupling to the elastic strain should drive it that way. I'll leave you with a last speculation, actually, that quantum fluctuations make this into an incommensurate domain wall liquid. And it will be nice to know whether you can do this, because these fluctuations from ferroelectric to paraelectric this way can be driven by temperature, and in principle they can also be driven by quantum mechanics. This might solve a number of puzzling conundra about a very enigmatic material, strontium titanate. And I'd better stop, because he's been waving more and more frantically, so I'll stop right there. So thank you.
Giving us a lot of puzzles.
Yeah, no, that's right. So I've left you with lots of puzzles, right? So that's right. A partial solution of some of them.
So do we have some very urgent questions? Because otherwise, I mean, remember that there is always the possibility of speaking with Peter outside during the coffee break. But perhaps there is one question. Yes.
I'll just throw one in when you were looking at the Ginsburg-Landau theory.
Right.
In a lot of cases, say, macroscopic quantities are renormalized by microscopic quantities,
sure.
Even the sound velocities in a
sure.
whole. So there is a microscopic parameter that is the energy that it takes for, say, the big cation to hop between one polarization state to the other. That is not there somehow.
Well, I say the point is, absolutely. I mean, so there's a lot which is not here, right? So where would I throw that?
Because it would change the dynamics.
It will say, it will absolutely change. So where would I do that, right? So basically, I spend a lot of time producing the interaction between the degrees of freedom produced by these long-range strain fields. Okay? I didn't worry at all about this thing, which is the local energy, and for that matter, if I put in dynamics, the local dynamics associated with that. And of course, that matters, right? So for the materials I'm looking at, I fit this. I didn't do microscopics. I didn't do anything about that. And of course, that really matters, because I just want to, because normally people think that this is the only thing to worry about. So I just need to demonstrate that that's true, but I'm certainly not saying that that doesn't matter. And in fact, I think, maybe my last slide would have been something like, oh, I didn't come out. My last slide is a question about, can you bring together the proper local many-body physics to describe all of those things that you have to do, and then couple it to these long-range fields. Now, by the way, it's not that the long-range fields wouldn't be in some ab initio simulation. They would be there. It would just be awfully painful to do them with ab initio methods, and kind of pointless, I think. So mixing those two approaches would be useful. Question?
Just let me ask a material-related question.
Yeah.
In these manganites, when the charge propagates,
right.
This octave distort. It's a distortion as you have shown.
Right.
So what is about the fatigue of these materials? Because I think the crystal suffers, the material suffers.
Well, so I mean, what I'll say is that up here it does. So to zeroth order down here in the ferromagnetic metal, and you can really see this as you go through this transition, the distortions really depleted. So this is more or less uniform electron gas. The electrons are in every unit cell. It's more or less cubic. But as you cross this line, you go into this thing which actually produces these local distortions. And so the fatigue is really associated with that.
So do the crystals break?
Well, so actually, if you look, so physically what happens as you go along this line, this transition is second order. There's a first order line, there's a first order point around here, and this is a first order transition. And the crystals can break if you do this, right? There is a very large elasto-magneto effect associated with this, which various people have tried to choose. Produces huge change in capacitance as you go through here. So these are very complicated multiferroic materials. And I say this is sort of a cartoon, and the only reason that I'm inspired to put up a cartoon is that actually it was this curve, although this is my fit, this plot really is from Paul Hatfield. So Paul systematically made very large numbers of compounds to try and understand this line, and derived not just the average change, but also the effects due to disorder. So it's yeah.
Okay, one very last question.
Sorry.
Quick one. You made a kind of an analogy between manganese 3 plus and nickel 3 plus.
Yeah.
But I was wondering, nickel 3 plus, maybe it's really nickel 2 plus and the oxygen.
Oh, well, right. So actually, so the nickelate here. So the story for the nickelate, you may notice that the boundary goes actually the other way. So what is that? I don't know whether this is nickel 2 plus or nickel 3 plus or whatever. What actually happens in here is that the nickelate ground states are dimerized. So that there are two different nickels per unit cell. And actually, so one is larger and one is smaller. And so this is coupling to breathing modes rather than the other kind of modes. But the breathing mode coupling, just to go back here, gives you, a different form of the coupling constant. Okay? Because again, you've got these local degrees of freedom, but they're not independent, so you get rid of the ones that you don't care about in favor of the ones that you have. But because they're all coupled, embedded in here is the same long-range interactions that you saw with the domain wall physics that I gave you, right? So it's, but indeed, nickelates are different than manganese. I mean, and by the way, I don't know what happens in the other series, but every single one of those phase transitions is coupled to the lattice.
Thank you very much, Peter.
Thanks.
Again.
Thanks.